All right, good afternoon. My name is Ali Kujuri. I'm an adjunct professor at the Engineering Science Department and one of the organizers of this lecture series. I would like to thank Mr. Sharam Marivani and also Ms. Kate Lapp, who in fact helped me organizing this series. On behalf of the Department of Engineering Science and the School of Science and Technology, let me thank you all, and especially our guest speaker to be attending this fourth lecture this academic year, and in fact 139th lecture in the series since we started in 2006. Two announcements before I introduce our guest speaker. Number one, pizza will arrive at 5:30, and I hope you join it. In fact, Kate has ordered the pizza. And then the next lecture will be on November the 1st, titled Fundamentals and Trends in Photovoltaic Electric Generation. It is given by Mr. Paul Henry. He is a senior applications engineer at Solmetric Incorporated. Our guest speaker for today is Mr. Benny Smith, and the title of his talk is LED Lighting, Cool and Bright. Mr. Benny Smith grew up in Texas and graduated from Texas A&M University with a Bachelor of Science in Electrical Engineering degree in 1966. He spent 2 years in U.S. Army as a second lieutenant armor. Benny attained teaching certificate in elementary education in 1971 and taught junior high math and science for 1 year. He then pursued graduate work and received his Master of Science in Electrical Engineering from Arizona State University in 1976. He worked as a design engineer at Motorola Semiconductor in Phoenix and moved to Sonoma County in 1976 to work at HP's Santa Rosa division. Benny retired from Agilent in 2004 and built his first commercial LED light fixture for Vision Smith in 2002. So let's just welcome him.
Push this button to go forward? That way,
Yeah.
Right?
The back, that one works better. For the back is a little
Okay.
yeah.
Glasses, there they are. Okay, so my company is Vision Smith. I'm actually sort of like a consultant for Vision Smith, and it is based in Santa Rosa, and that's the CEO. Looks like he's about your age, doesn't he? How old do you think he is? Take a guess. 30s, 40s, 50s?
30s. 32.
Say again.
32.
32? One more guess?
Early 30s.
He's 48. So that picture was taken early this year on the floor of Sonic Manufacturing down in Fremont. They're a contract manufacturer and they make our stuff. They make this thing that I brought with me. I'll show you here when we produce that. So, Ali already told you all of this stuff. And that's the way it went. I really have only worked about 3 places my whole career. And I've worked most of it at HP. So I picked up things along the way. And there's one critical skill that if you're able to acquire this skill early, you'll be successful. If you don't acquire it early, and it takes you a while, you're going to be sorry. That's just the way it is. And that skill is, oops, sorry. Got ahead. I wanted to tell you something about me, so I decided to show you a picture of my hero. Because if you ask somebody who their hero is, it tells them a lot about who you are. So let's see if you can figure this out. Who is this? Whoops, back, sorry.
Yeah, use the other one, as I mentioned,
Okay.
it didn't work very well for the backward, yeah.
Who is this? Yes?
Richard Feynman,
What did Richard Feynman do that made him famous?
quantum electrodynamics.
Yes? Nobel Prize. American, born in New York City. And there's a bunch of things about Mr. Feynman. That's a picture taken right before he died in 1986. He's one of the most innovative and humorous-laden scientists who ever lived. He wrote a whole bunch of books, and there were a bunch of books written about him. I recommend you read them. He was very inspirational for me. And one of the things that I never can forget about him is that he said when he would come home from school, his mother would always ask him, he got tired of it, she would always ask him, "Did you ask any good questions today?" That's all she wanted to know. And she expected him to answer. And pretty soon he got the idea that that's what she expected him to say. So here's a statement from Mr. Feynman. So here's the critical skill I'm talking about, that if you have it, you can open doors and you'll be successful. If you don't have it, I don't think you'll be very successful until you get it. So you might as well get it early. It is asking the WFQ, not the WTF, the WFQ. What is a WFQ? Here's my definition. It's a well-formed question. It has just enough to get the information that's desired and no more. It's not wordy, not long. The worst example of a well-formed question, or that question that's at the other end of the spectrum, is, I'll say it in quotes, the question, huh? That's the most useful question sometimes, but most of the time it isn't. A well-formed question is what Mr. Feynman was all about. And when I read his books and I read about him, it quickly occurred to me that it was right. And I taught for a year in junior high, kids that are 10, 11, 12 years old. And I observed that those kids who had that skill already were able to learn anything they wanted to. So really, that's the key. If you can do that well, you can learn anything you want to, especially nowadays with information pouring out of every porthole in the society at you. So, answers are available. Okay, so I'm going to leave this up for a second, and I'm going to ask you another question. But first, I want to introduce you to a friend of mine. Would you pass this around? This is obviously an LED. It's a little green LED. If you look at it, some of you can already tell by looking at it, it has two batteries in series, and it's an LED. So if you've had a circuits course, tell me what happens if I do this. And let's make the voltage of this battery a good size. You pick 5 volts, 10 volts. On the right is a regular silicon diode. What happens if I do this?
Essentially a short.
Yet a short circuit. Will the diode survive? No. What you have there is two 1.5 volt batteries. That makes 3 volts in series, hooked across an LED. It's a diode, isn't it? Yes? Why is it surviving?
The resistance of the wires.
What's different about it? What's different about it?
The resistance of the wires.
Right. Well, anyway, I'm not going to answer that one for you. It's a lot of fun to explore on your own to find out why. There's good reason why an LED, which has the only difference in the symbol is that. We draw that to show that there's something coming out of the LED. All right, so here's how I like to think about, and this is how you'll have to think about it too. Here it goes. I'm going to draw it big because I know there's somebody sitting in the back there. If you want to think about an electronic element, you're always interested in V and I at the same time. They exist together. So you think of a VI plot. Some people turn it around, make it an IV, but I draw it this way. So I'm going to put something up here. I'm going to ask you a question. I'm going to draw 3 curves. I want you to pick the one that represents a resistor. Okay? Now this is current versus voltage. Okay, let's pick on somebody. What do you think it is? Which one represents a resistor?
B.
B? Okay. Anybody have a contrary opinion? Nobody? Everybody thinks it's B. That's good. Somebody's been successful at teaching you guys. All right, so now the next question is, well, I'll just draw it over here. I hope I draw it big enough. There's a battery, there's a resistor. So current's going to flow like this. There's going to be a voltage here. So I'm going to represent that as I, and this is V. And so those could go right on here. So I'm going to take your word for it that this one is the right choice. That setup will result in 1 current and 1 voltage across the resistor. So how would I represent that on this VI curve? As another line? As a curve? As a point? How would I represent it? Question. How would I represent it, the operating point? That situation, battery, resistor, on that VI curve, somewhere, I want to know where am I, what's the value of V and I? There's only going to be one value of each. Where's it going to be? It's going to be on that line, right?
Yeah.
That's what you told me. Where's it going to be on that line? We don't know because I haven't given you values. Okay, so let's just assume it's here. All right? So, if that's what we call an operating point for that little system right there, that little VI system. So, if the resistor value, see, we're all set up now. We got a setup. If the resistor value goes up, gets larger, where does that operating point go? Okay, I'll give you a choice. I'm going to put a higher and a lower, H and L, resistors in. So, and I'm going to give you a choice. And I'm arbitrary here. I don't know if I got that right or not. But if I increase the resistor, where does the curve go? Does it go up or does it go down?
Go down.
Why does it go down?
Because as your resistance goes up, the current's going to go down with the same voltage.
Okay, you agree with that?
Yes.
Okay, so if I go down in resistance, that curve will go up. Okay, so if I redrew the curve, actually what will happen is, it looks something like that. Okay, so that gets us ready to talk about the LED again. And so let's do the same thing we did before. Let's see if we can figure out what an LED's characteristic looks like. So I'm going to draw 3 curves again to see if you're following me. And they are A, B, C. Which one is it? A? That's the curve of voltage and current for a LED. Everybody agree?
Yep.
Okay, so here's what I know about an LED, and I'll show you in a minute. When I put voltage across it, nothing happens for a while. And when I increase the voltage, and I keep going, suddenly, with an LED, it'll turn on, like this little guy right here. So that means I wait and I wait and I wait on the voltage axis, and then finally I get something to happen on the current axis. Now, if it were A, then I would have to wait and wait and wait before I got any current. But here, I get current right away on A, right? The minute I come off of 0 volts, I start to increase the current. Does that sound like an LED? No. So it may not be A. Another nomination?
It's B.
Say again?
It's B.
B. It's B.
Diode curve.
How many agree? Okay. Anybody disagree? No, I don't disagree either. So I think that that's true. I think that B is the correct curve for an LED. Sorry to belabor that, but it helps to know that. So, if I do what I did before, and I take the resistor out, what I'm going to put in here is not a diode, but an LED. And I'm going to indicate that by these little arrows. So I don't know how much you know about LEDs or how much you played with them, but they're sort of like a diode, very much like a diode. So on this curve right here, let's suppose that curve represents the operating conditions of this thing here. On that curve, where's the operating point? Remember back with the resistor, we had an operating point. Where's the operating point on this one? Tell me where to put it. I'll start here. Move to the left, move to the right. Move to the right.
Keep going.
Okay, stop me when I get to the right spot.
There you go. I mean, it's still good there, but yeah.
We gonna burn it up?
No.
Yeah, you want to go back to
Okay, all right, let's just put it here. Oh, think about it for a second.
Good plug.
We talked about operating point of the resistor. What does it mean? It means the single point where everything in this little system is satisfied. The voltage, the current, and the internal. This thing has sort of like internal resistance, almost like a little built-in battery of its own. So if I do this now, you see where I put the operating point? That means that this LED is operating at this current right here, call it IL. Now I'm going to make a change and I want you to tell me what happens. I put a resistor in there. If you like numbers, I'll just put in, it doesn't mean anything because I didn't give the other ones values, but it's not a real big resistor. It's a fairly small resistor. Where does the operating point go? This is just applying to the LED now, okay? This just applies to the LED, not to the whole system. So this is LED operating. That means current and voltage in the LED. Where's the operating point go?
Drop the
Okay,
voltage.
better question. What happens to the current?
It's going to drop.
It's going to drop.
The
Why?
voltage across the LED.
Resistance. Okay, so if the current drops, the LED doesn't care how that happened. It just knows it doesn't have as much current anymore. And so the operating point has to come down on that curve, right? That's what happens. Okay, so that's good. Need to know that. So next, I want to show you evolution. You may already have done this yourself. I'm a flashlight collector. So 10 years ago, I bought this Streamlight Stinger. It was the cat's meow. This was the neatest flashlight, brightest flashlight that you could pack that was this size. And so, look at it. Everybody can see it? Let's put it here in a dark spot. See that? That's 10 years ago, that was hot stuff. Okay, so now, this little LED light I got this in my stocking last year at Christmas. Now this is fairly recent. This is probably 2 years old. This design is 2 years old. And it's, look at it. You see what's going on there? Take a look at that. What's going on there? Why does it look like that? Okay, the reason is that's the chip. That's the collection of chips that are putting out the light. And the lens is so accurate at rendering reality, it's given us a little picture of that chip. So if we defocus it a little bit, now we get a flashlight. So that's not so hot. This is a single AA. This is a battery that Streamlight sells, and it's expensive. It's 20 bucks just to buy the battery. And it's really nickel cadmium. It's like 3 or 4 cells. I forget how many. Okay, so here's a light that I bought. Kind of big. It's got 2 AA's in it. This is about 5 years old. So, and it's got 2 settings. So, okay, it's a little bit nicer in the way of a spot. You can spot something, but it isn't really very bright. So this is 2 AA's and 5 years old. So, oh, and it's got a little blink mode, so if you lose it. Okay, so here's something my son gave me last Christmas. Wasn't in the stocking, but it was a little box. And he knows I love flashlights. So here's this thing. Now this has a 3.6 volt lithium battery in it. It's really lithium compound. But now it has 5 settings. So watch. That was top. There's 1, 2, 3, 4, 5. Oops, sorry. So that's a hell of a light. I don't know if you can tell that, but you can do a lot with that. And I do everything with it. In fact, at nighttime, so I don't keep my wife awake, I read with that one. And it doesn't bother any. So, I'm sorry, I read with that one. Okay, so I just wanted to point out how fast this stuff is changing and how you have to pay attention or you miss it. So here's another example. It's my last example. No, it's not my last, almost my last. Here's another little, I bought this LED at a swap meet. I don't know if you can see what it looks like. It's round, but they call it a star pattern. It's made by a company called Luxion, and it runs off of 3 volts, 3.2 volts. So I have 3 alkaline cells, nickel metal hydride in here. So look how bright it is. That's a lot of light there. Now, this little guy here, this is 3 volts, okay? And these batteries don't have as low an internal resistance, but this is 3.4 volts, and there's a lot of difference in brightness. So, now this is, you can buy these are indicators. These are not. These are supposed to be used for flashing things. But here, I'll just pass it around. Don't look at it. When you get through, I'll take the battery out. Okay, so this thing, let me turn this off. This is the sort of thing that I'm interested in. This is an old fixture from Hollywood, and it is, these are hanging all over the world, especially in Hollywood. They had halogen bulbs in them, and they consumed 1,000 watts. So it's called a 1K, meaning 1,000. And it's got a Fresnel lens on the front of it. The Fresnel lens allows you to focus it from wide to spot. And so there are techs and light guys called gaffers in Hollywood that spend their time on ladders adjusting these. And they also have to change the bulb about every 100 operating hours. So they were looking for a way to get around that, all the difficulties and disadvantages of having an old hot light like that. So they wanted to replace, where's my button? There it is. They wanted to replace this thing. I don't know if I can give you a perspective, but that's about 4 inches tall. And it's a glass bulb. It's got halogen inside the, it's a gas inside the envelope. And when you turn it on, it eats 1,000 watts, and it's pretty bright, fairly bright. So this,
I'll return this.
okay,
Take the battery out.
what you see sitting here is the first product that we made. It technically replaces that one, but I'll tell you a little bit more about that in a minute. We didn't know that this was a big deal, replacing all these old lamps. We didn't know that when we started. So we built this one, and it consumes 150 watts, and it's got a display on the back of it that allows you to adjust the, as you can see as I'm turning the knob, intensity's going down. So it's got a linear control, and the firmware has some features that make it really attractive to photographers. One of which is, if you push the button, you get a readout of stops. If you're a photographer, you know what I'm saying? One stop is a change in light intensity of 1/2. So like a dB scale. So if you're used to thinking in terms of that, and you're working, you're taking pictures, and you tell your guy who's running the light, drop that light by 1 stop. So all he has to do then is dial this in till it says 1.0, negative 1.0. Now he's halved the amount of light that's being put out. So it's a useful feature. It's got a bunch of things. When we're through talking, if you want to play with it, you can look at it. But I'm going to talk about this, because this is where we go from here to close to that. It's illumination. It's about illumination. All right, so I'm going to move this over, turn it down. You can see it. So this is a comparison on the screen between halogen and LED. So the example I'm taking is we wanted to replace that thing I showed you, that Mole Richardson 1K Fresnel. It consumes 1,000 watts. We only wanted to do 150 watts because we heard that LEDs were about 6 or 7 times as efficient. So if you multiply 150 by 6, you get 900. So with a 150 watt LED, you ought to be able to equal a 1,000 watt halogen. And not only that, you wouldn't have all the heat. You wouldn't have 1,000 watts to get rid of. Very attractive. So the halogen bulbs were really too hot to handle. You had to use gloves if you had to handle them right after you got through shooting. Whereas the LEDs are cool to the touch. You can handle this one. The light was restricted. I don't know if you know about color temperature, but 3,200 Kelvin is kind of yellow. And that's what halogen bulbs put out. That's their natural hue. When they age, they get yellower. And so that's another pain in the ass. If you're a lighting guy in Hollywood and your bulbs are kind of old and you have to shoot, you don't have time to run up the trolley and change them, you have to use color gels and put them in front of the light to correct it, to get rid of the extra yellow that you didn't want because the light was old. And so that drops the intensity of the light. Everything you put in front of the light drops the intensity. So now you gotta move the light closer. You gotta tell your actors to stand closer, whatever. Pain in the butt. The LEDs come in a lot of different colors, and the most popular is 4000K. It's kind of in between. 5600 is kind of bluish, kind of daylight, and 3200 is definitely yellow. It's when you turn your light on in your bedroom at night. If you look closely, it looks a little yellow. That's about 3200. That's what I'm talking about. So if we want to design a replacement, we have to start somewhere. The first thing we have to do is say, bulb life. 100 hours versus 50,000 hours. So you plug the LED in and it stays plugged for a long time. You have to change it. Okay, so this is what I call Hexa Lux. This particular model, if you look on our website, this is called the Hexa Lux. So when we set out to build this, we had some design requirements. What do we want it to do? So I'll just go through them. We wanted it to be equivalent to a 1K halogen. That was our target. If we couldn't do that, nobody would buy it. Well, in fact, we make some that are smaller than that, but that's the sweet spot. Tens of thousands of lights that are hanging in studios and TV rooms all over the world are basically that size. That 1,000 watt halogen bulb put out the sweet amount of light that everybody could use and everybody could afford. So everybody bought them. I mean, there are bigger ones, yeah, for big studios, but that light was the target. So we were doing the 80-20 rule, you know. We want to hit 80% of the market with whatever we come up with. So we wanted the original, this one, to be powered by DC because we were going to make it small and portable. If you have time to go to our website, you will see on there a testimonial that a videographer made out of the blue. We didn't even know he was doing it. He does it for a living, but he made one about our light, and we posted it on the website. And he talks about how nice it is to be able to have battery power and be able to put it where he wants it, unobtrusive. So we wanted to be able to power it from the wall or from battery, either one, on the go or in the studio. We also wanted full range dim control. Obviously, everybody wants that. You want to be able to go way, way down and all the way up. And we wanted to be modular because we wanted to be able to, if you look at the website again, we wanted to have a different abilities to project light. So this is a 7-inch front end. If you look on the website, there's a bigger front end. It allows you to have more spread and actually makes it look like there's more light. And there's a demand for that, so we make that also. So that makes it modular. Also, the battery fits on the same stand as this thing. And I say this thing, this is a metal case that we make. Inside this metal case is a really superb 20-volt power supply. It operates from 90 volts AC to 240 volts AC, so it's worldwide. It's made by a company called Meanwell, and it's absolutely fabulous. So we couldn't do anything better. We bought that. We have battery options as well, but I didn't bring that. I wanted to show you this one. So we want to have a zoom Fresnel, because that's what we're competing against. We want it to go spot and wide anytime we want. And we want it to be DMX compatible. If you don't know what DMX is, raise your hand. Okay. So DMX is a digital control signal, and it is daisy chain. So it's used by lighting people in studios, a lot in theater, less so in real movie studios. It transmits a digital 8-bit word repetitively, and if you're receiving DMX, you count how many of these words you see. And so there's 512 of them in a series, and then it starts over. So if you're a receiver on the line, you're in a long daisy chain. You might be down near the end, you might be at the front, but it's like a daisy chain going from here to Katati. Somewhere on that line, you plug yourself in, and whatever your doodad is, say it's that, you've assigned it an ID. And the ID is simply the number of the word on this chain of 512. So you might be 237. So your gadget starts counting when it hears the start, and it counts 236. And on the 237th, it says, wake up, we got to count. We got to remember this. And it captures that 237th 8-bit word, and that tells it one of 256 levels of intensity, if it's a light, that it can go to. 8 bits, 256 values for an 8-bit word. So, yeah, this thing's not doing well, anyway, it'll be okay. Ignore that. So, we had to pick an LED for this. So these LEDs I showed you, all these flashlights and everything, this is not 150 watts. This is the brightest thing well, maybe this flashlight. This might be the brightest thing I showed you. One or the other of these, and they're on the neighborhood of 7 to 10 watts. We want 150 watts. So where do we get something like that? So we started looking. And at the time, Bridgelux, a company called Bridgelux, was the place that had the best LEDs. And this is what they had. Can you see that? Everybody can see this. You can't see it because you're too far away. But there's a whole bunch of little dice, little semiconductor dice. They're LED emitters is what they are. And they're all arranged in row and column. And they're all hooked together in just a certain way so that the voltage I need to make it really bright is between 30 and 36 volts. And so I got a power supply here that I rigged up for this. And so you saw what these look like. And you saw what this looks like, although this has a lens on the front of it. We go up. There's what a flashlight, a state-of-the-art flashlight looks like. Actually, there really are brighter ones, but. So this is what we're after. And this isn't 150 watts. This is about 120 watts. And I'm getting tired of holding it because it gets hot really quick. So that's what we were after. And we found it. Bridgelux had it. So I started with this, and I started figuring out how can I drive this. So here's the problem. I keep losing my sponge and my marker. What do I do with it? There.
The sponge is there.
Here.
Near the cube.
So the issue is this. I'm going to draw the LED like it's just one diode, although it's really an array. Here it is. And Bridgelux tells me, and I measured it myself, that let's say it operates at 36 volts. Actually, more like 42, this particular model. Okay, so, and over here, I told you already what we wanted. Our design requirements, we wanted to be either a 12-volt battery, or we wanted to be a 20-volt DC supply made by Meanwell in that case there. One or the other of those. So that is the input. The question is, what do we put in the middle? Forget about the control and the DMX and all that. What do we put in the middle? Give me a suggestion. How can we get from, let's just do the easy one. The easy one is 20. How do we get from 20 to 42 and supply 150 watts? This is DC, right? DC in, DC out. We can't use a transformer. Any idea? Say the word. Say the words. Tell me what it is. Okay. I'll answer it for you. And you'll do all the research later. First of all, I want to show you something here real quick just to jog your memory. You know, we were talking about this before, right? Remember that? That can be described very easily by this little algebraic equation that says V is equal to I times R. And so that's why that was a straight line on our characteristic curve, because that's a linear equation. So let's look at these for a second. This is an ideal inductor and an ideal capacitor. So what's the characteristic curve for one of those? Let's suppose I pick the inductor. What's it going to look like on this curve? I versus V. If I hook it up to a battery, what's going to happen? It's an ideal inductor. What's going to happen? What's the resistance of an ideal inductor?
Zero.
Zero.
DC at zero.
And that, what's the resistance of an ideal capacitor?
Infinity.
Just the opposite. Those two love each other. L and C, they're made for each other. They're just the opposite. So notice this about the resistor versus these. If I'm talking about current, then how how did I, make sure. Um, What does that mean? Okay, so with an inductor, current has to be continuous. You've heard this. If I try to change the current in an ideal inductor, instantaneously, I get a huge voltage. And I'll write it down for you in a second. Whereas the voltage is discontinuous. That is to say, if I try to change the current in an inductor, instantaneously, the voltage can go wherever it has to go, but the current can't. And the capacitor is the dual of that. With a capacitor, the voltage is continuous. I can't change the voltage across a capacitor instantaneously. If I do, I require an infinite amount of current, so the current's discontinuous. So keep that in mind, because that is the reason why we can do this right here. I ask you the question, how do we go from 20 volt DC supply to, how am I doing?
Well, you have 15 minutes.
How many?
50.
15, okay. How do I get from left to right on that diagram? If I don't do that, I don't have a product. Okay, so the way I do it is with an inductor. And I'll show you how. This thing I'm going to draw is called a boost converter. L is the load. I put a capacitor here because we need it. That looks too simple, but that's exactly what it is. That's how this thing works. That's what's at the heart of it. So, is there anybody here who knows about a boost converter? If so, raise your hand, and I'll speak at a higher level. Anybody here know how a boost converter works? Okay, so it's really very simple, and it takes advantage of the inductor, naturally. So, this is a switch. So if I put a voltage in here, let's say it's 20 volts. If I put 20 volts in here and I close the switch, there's a current that flows here. And forget about that for a minute. If I leave it closed long enough, whatever resistance is involved here, the current's going to get to be wherever I want it. And I actually have a lot of control over that. So let's suppose I close it for a while, and then I close it, and then I open it. When I open it, the current in the inductor is going in this direction because the voltage was forcing that. It wants to continue to do that. And I can't stop it unless I'm willing to absorb a huge voltage penalty. So what happens is the current goes this way, through the load, through the capacitor. And then I close the switch again. Oops, I left something out, sorry. Who recognized that I left out this important component? So let's pretend that this doesn't have a lot of forward resistance. So when the inductor is passing current, goes through the diode, no big deal, not much loss. Most of that, well, all of that current, and most of that voltage gets to the load. When I open the switch, that happens. When I close the switch again, now I've shorted the inductor to ground, and that means that the diode's now back biased. It's reverse biased. It won't carry any current. So whatever's stored in the capacitor and whatever was flowing in the load, the capacitor now becomes the source for the current in the load. And so if I close and open that switch at just the right rate, I can get whatever voltage I want out here. Because, and if you follow me on this, you'll get it. If have you had calculus? Okay, so you know about dIdt, you know about derivatives. You also know about inductors. You've had a course and they told you this, okay? This little table I had over here that showed the funny characteristics of L and C, I left out time. That's what's important to those two. So the voltage difference between the input and the output is absorbed by the inductor. So the three of them add up to 0. So if I'm clever and I choose the value of L and T and I can get the voltage I want at the output. What I want is 42 volts for my LED. And I can get it just by using a boost converter. Okay, so now here are some tips. Once I get that LED wired up, I have to keep it cool. If I don't, it melts. The old halogen lights do not care how hot they get. In fact, they love to get hot because you have to use gloves. You have to limit the forward current. There is a point where you will carry too much and you'll burn the thing up. So you gotta watch out for that. And you also have to prevent reverse breakdown because everything is mortal and they have a reverse breakdown. Okay, so here is the Hexa Lux block diagram. Let's see if the laser works. What did I do wrong? It does. Can you see it? Oh,
No.
now I can see it. So here's the Hexa Lux block diagram. This is the thing we're calling Hexa Lux right here. There's the block diagram. That's what we ended up with. When we had that block diagram, we said, now we can start doing things. So there's the boost circuit I talked about right here. That's the key part. If that doesn't work, forget it. So we have 42 volts. We have to feed it through a control mechanism so that the LED gets how much we want. Because you saw me turn the volume up and down. And then there has to be a 5-volt regulator coming off the front to run all the electronics that are on board. There's a microcontroller in here. Now here is the controller, and its inputs are the rotary pulse generator, the RPG that I was twiddling. The DMX comes in through a decoder and it goes into the controller. And there's a heat sink, obviously, because the thing's getting hot. And there's a temperature sensor on that heat sink, and that's feeding the controller. And then the controller's outputs are to a display, to a DAC, and a fan control. We wanted to use a DC fan, so we had to convert a digital value to an analog value to drive the fan. So that's the block diagram. The LED we ended up using after about a year, was that's funny. Okay, so I've screwed my slide progression up here. First time I've given this talk, can you tell? So that's the Hexa Lux block diagram, and it all comes down to this. I'm going to pass this around. That's it. That block diagram ended up in this little board. It's basically single-sided. Everything's on one side. It's mostly SMT. But that's what runs this little thing right here. So you go from block diagram to a finished product in about, actually it took me, I started working on this sort of cold in the middle of April. My son went to Las Vegas and came back from a show and he said, this little bitty thing we built, he said, we can't sell that. We gotta have something like this. We didn't know what this looked like. So I started working mid-April, and then on Labor Day we had a celebration, we had a finished product. So I worked the whole summer on it, working with him. And so after Hexa Lux, it occurred to us, somebody had to tell us this. There's all these old legacy lights hanging up all over Hollywood. Well, my son knew about it because that was his business. He said, oh, I forgot about that. I didn't know what he was talking about. He happened to have one in his closet. He took it out and he brought it over to my house. And he said, this is it. And I said, oh, so we have to replace that bulb. And you saw the bulb is really pretty small. It's located in there at the focal point so that there's a reflector and the light comes off of the bulb, kind of, like in a sphere pattern. It hits the reflector and magnifies, so you get a useful light out of that thing. So he said, this is what we have to do. So that is what we were shooting for in 2014. In 2012, we introduced the first one. By 2014, we realized we got to do something with this if we want to make any real money. So we called this thing relamp, meaning relamp, you know, redo the lamp. So here's the design requirements for this. You saw them for the other one. For this one, it's got to be a drop-in replacement, period. You got to pull the old bulb out, put our thing in, close it, you got to be done. No changing, no taking a reflector out, none of that monkey business, nothing. So it's got to be LED clearly. It's got to have that same light output that the Hexa Lux had. It's got to be equivalent to a 1K halogen. And the power, now here's the tricky part. The power input is 95 to 240 or 250, what I put down, 250. It's got to work worldwide. That is a tall order. I don't know if you've ever designed, well, you probably haven't, but those people who have designed something to work at that power range, and they're all over the place. You can buy them at Walmart, little bitty things that'll plug in worldwide. It's a real challenge. It doesn't look difficult, but it actually is. That kind of makes it fun, but. And it has to be compatible with phase-controlled dimmers. You have light dimmers in your house somewhere. You've got one on a lamp someplace, and you use it to dial up the light at night or dial it down. That's a phase-controlled dimmer. And it works by, it's a cheating mechanism, really. It works by, I'll show you in a second, it works by changing the phase of the AC. And also, this thing has to be focus compatible, it has to work. When we stick it in there, the light source that we're sticking in there on this module has to be on the same exact location that the bulb was. Because if it isn't, the Fresnel doesn't work. So we got to design it so that it will. So the trick on relamp was, how do you get 150 watts of DC power from 95 to 240 volts AC input? Why did I say DC? DC power. Why?
LEDs work best in DC.
Because that's all LEDs will eat. They won't eat AC. So even though this is an AC device, it plugs right in the wall, I know I'm going to end up providing DC to the LED somehow. I got to do it somehow. And that's the tricky part on this one, is doing that and doing it well. And with a phase-controlled dimmer between the wall and the light. Because everybody in Hollywood uses phase-controlled dimmers. When they dim down for a scene, they've got this guy, this lighting guy. He's sitting in a box about this long, and he's got these sliders. It looks like a studio in a concert. And he moves, he knows where they are. They're all marked, they're all calibrated. He moves the sliders, and those are all dimmers. Every one of them is a phase-controlled dimmer. And they're really hard to use with an LED, because an LED has a microcontroller, and it cares about noise, and it's awful. So, but when the old days, when they had halogen bulbs, the halogen bulbs didn't care. All they care about is power. They don't care what it looks like. So phase-controlled dimmers work. So the Hollywood studio said, if your thing doesn't work in a stable way and do what it's supposed to do with a phase-controlled dimmer, we won't buy it. And so that turned out to be one of the biggest challenges we've had, is to make our thing work with this crappy old dimmer that shouldn't be used anymore. There's better ways to do it. But everybody in Hollywood has trillions of dollars invested in them, and they said, well, we're not going to buy it if it doesn't work. You know, this is what we have. So that's what a phase-controlled dimmer does. The waveform on the bottom is what's coming out of the wall, and the waveform on the top is what the dimmer does. And the dimmer does it in a really, it's super crude. I've lost myself again here. It's really crude, and it was invented probably, well, after solid state came in. Before that, it was all done with tapped transformers. But essentially, this is what it amounts to. There's the AC input. There's a load. I know you can't read this in the back, but I'll read it for you. It says control. That's all it is. The AC is hooked across the load, in series with the load, and this thing right here, this is a triac. It's like an SCR, a silicon control rectifier, but it works in both directions. So you can trigger it one time and it'll go with a positive waveform. You can see that here. Both positive and negative halves of the power get through. So by moving the slider, you get that kind of a control. So this is the final headache that we had in making relamp work. Relamp, remember, is this thing. This is what we ended up with. That is the Hexa Lux. This we call the EGT, and we call it that because that bulb that you saw earlier in the relamp, that has an industry name of EGT, and then we wanted to mimic that, so we just started calling this the EGT because that's what we were trying to replace. So this is the EGT. This goes in one of those fixtures that I showed you, and I'm going to pass it around. You can see what it looks like, but I'll just give you a clue. It's all about heatsink. That's all that's really going on here. Well, there is some other stuff. The compatibility with the phase control dimmer. But if you look at it, look at the bulk of it. It's a gigantic heatsink and a big fan. And why? Because this sits inside that metal can, and it can't get rid of hardly any of its heat. And so it's got to work really, really hard to stay alive. And that's just the nature of the animal. So this is what we settled on. This is the biggest thing we could get away with. We tried to go as big a fan as we could get because we want to cool it. We want to stay alive, but it's got to fit in that can. And so it was a cruel compromise, and I worked for months trying to figure out how to do this. And I did finally, and it works fine. It works great. We sell a lot of these. But here, pass it around, take a look at it. That is a relamp. That's the middle, and that's equivalent to the Hexa Lux. 150 watt consumption and equivalent to a 1,000 watt halogen. And if I could turn it on for you, and you can see what I'm talking about.
And
Actually, I didn't bring it to you.
There too?
Say again?
The circuit board that we just passed,
Yes?
is that part of this whole thing?
No, it isn't. It's part of this one. It's a Hexa Lux board. This board is exposed, as you'll see when you touch it, so you can see what's going on here. I brought this because you can't really see what's inside this one. It's all buttoned up. But anyway, that's all there is. And an LED, of course. Okay. How am I doing? I'm over.
Yeah.
Okay.
It's now the time to ask questions.
Questions?
Question,
Yes.
what's the toggle frequency on your switch?
For the boost control,
Yes,
it's about 160 kilohertz.
okay. So there's going to be flicker in your light from the variations, but that's a frequency that doesn't affect anybody.
No, but we do have flicker problems.
You do?
Yes, we do. And the problem is, you don't mind getting into a little detail, I guess, right? Okay, I'll tell you, this is really not a trade secret, everybody knows about it, but the problem with flicker is the 60 hertz.
Yes.
So 60 hertz, you can't really see it unless you're really good. If you're a special person, you can see 60 hertz flicker. Most of us can't. 120 hertz is if you full wave rectify the line voltage. Nobody can see that. So you would ask, well, heck, I can't see 60 and nobody can see 120, so why do you have flicker problems? I wish I could tell you, but we have them, and they emanate from all the interactions of real-world electronic components. It's funny, when you start sticking real stuff together and trying to make it work, you find out all kinds of things you didn't know about inductors and capacitors and resistors. You know, you're blindsided. It's great, it's a lot of fun, you learn a lot, but you know, if you're trying to get something done, you get frustrated sometimes. So the flicker that we see is related to 60 hertz. And it's also related to the fact that these devices have to have electromagnetic compatibility with the outside world. So they have to have a filter on the front end of them so that any nasty electronic garbage that's being created inside, let's say inside relamp, anything nasty that I'm creating in there, I'm not allowed to send it out onto the power line Because if you're watching TV, it might come into your TV and screw it up. You'd say, all right, who's got a relamp in this neighborhood? So I can't do that. That means I have to have an EMI filter, called EMI, electromagnetic interference, to keep that garbage from going out to the world. And the problem is that that EMI filter interacts with not so much the line, but the dimmers, those pesky phase-controlled dimmers. They're not perfect. In fact, most of them are not very great at all, electronic design-wise. They're very crude. And they put crazy stuff in there to compensate for it. And they don't care, because they didn't design them for me. They designed them for the halogen bulbs. So that phase-controlled dimmer is responsible for a lot of the flutter issues that we've had. We don't really have any now. I beat them all.
You're getting a subharmonic of a 60.
Yeah, of course.
Yeah,
Yep.
yeah.
Yep. Subharmonic. Other questions? Come on, you're college students. You're worried about money. How much do these things cost? What is a Hexa Lux cost? Who's cheated and gone to the website? Nobody yet. We started off selling it for a little under $2,000. And so when my son Pete told me that, I said, we'll never sell them for that. That's too much money. He said, listen, you don't know anything. I already knew that. So you don't know anything about the business. That's what people pay in Hollywood for a new light. And he said, in fact, our competitors, I have to say, they're not as good as we are quite yet, but they charge more. The biggest name in the business is a German company, and they're called Aries. And they're the best. They really make the really nice stuff, and everybody knows it, and they're really expensive. So Aerie had a light that was similar to this one, but didn't have the flexibility. It had the output. That's all. In the beginning, that's all people thought you wanted was output. And it was $3,000. So when he told me that, I thought, oh, maybe we can sell some for $2,000. So we have. We sold a bunch of them for $2,000. So how about, where's the relamp? There it is. What do you think that sells for? Now that goes inside of another fixture, and once it's plugged in, you never see it again. You don't care if it's pretty or ugly, you just want it to work. So what do you think that's worth? What would you pay for that? $2. Okay, Mike, give $4.
98.
It's a couple $100.
$6.95. So when Pete said $6.95, I said, you're crazy. And he said, you don't know anything. Let me tell you. If you look at what happens when you replace a halogen bulb with this, there's a great spreadsheet that he developed on the website. So if you're interested, if you have any thought of doing your own business or something like that, check out the website, because he's done a really good job of this. There's a spreadsheet there that goes through the trade-off in dollars of keeping your old halogen fixtures running, and they're a pain in the ass, they're hot, and so forth, and going with relamp. And so some of the factors are, you put the relamp in and you don't mess with it anymore. So every 100 hours, you don't pay a union guy to get on the ladder and climb up and change the bulb. Don't do that anymore. You don't have any air conditioning bill anymore, because those old 1,000 watt lamps hanging in the ceiling, get about 12 of those going, you got to start the air conditioner or your actors are going to sweat you out. So you don't need that air conditioning anymore because you're not developing any heat. You're not replacing them. They last for 50,000 hours, so you're not out any money for that. So there's 3 or 4 other factors. When you throw that in and you show it to a customer, what the spreadsheet does is it starts at the top and shows how fast can you pay off a relamp replacement. If you just go over to it today and don't use the halogen anymore. So you still got the old fixture, okay, you're keeping that, but you're just not plugging those lights in anymore and paying that air conditioning and paying those union guys. You don't do any of that anymore. How fast do you pay it off? That's what everybody who wants to buy lights cares about, you know, because they have a budget. And they say, well, we like the relamp, but I don't know if we can afford it. How much does it cost? And Pete says, $6.95. And I say, oh, God. And then he says, look at the spreadsheet. And they look at it and they say, yeah, you're right, I do spend all that money, I do all that, I never thought of it, I never added it up, and there it is. And then most of them will say, shoot, it's a good deal, you know, so if I can get a loan someplace and buy or whatever. So that's been a really strong incentive for people to buy the relamp because it's a lot easier. It's upfront money, and it sounds like a lot. $695 for what? For this? But yeah, it sells for that, and people are happy to get it, and they're willing to wait, believe it or not. So it works. Any other questions?
Yeah, Benny?
Yeah.
We have a lot of, shall we say, sport field at night, like, you know, baseball and so forth. And then those, I mean, there's one right behind our house, and these light fixtures are really huge, and, you know, they go, of course, high in the town and so on. You sell these things to them because they also need them.
They do, yeah, they do. I'll give you a business card, you can hand it to him over the fence.
Right, yeah. But how many of these do you, I mean, have you sold so far?
Oh, let's see, we probably, of this particular one, we have probably sold 2,000.
Okay.
Yeah. It's probably more than that. I don't really know. I hate to admit it, but I just hide away in my hole and do this electronics. Pete is about 80% of the company. He's the marketing, he's the sales, he's the customer support, so he has all that at his fingertips. And, you know, you can call him anytime, send him an email, he'll answer. But I think it's between 2,000 and 3,000 so far. Actually, the one that's most popular is called the FRK. And that's because the little bitty bulb that goes in it, it's called an FRK. And that one goes in these little bitty tiny lights that a lot of amateur videographers and people use, because if you buy a consumer light to do your photography business, you're going to be disappointed because they just don't do anything. But if you buy an Airy, it's called an Airy 650, and it's about that big, and we make a module that drops right in. It's called an FRK. And those are really popular because everybody wants them. They're small, they're compact, they travel, and there's just a jillion of young people out there trying to do their own photo business, and they know that if they have a really good light source, half their battle is over. You know, you got to deal with the people you shoot and everything else, but if you don't have good light, you're not going to get a good result, period. And so that's why Airy is in business. They make really good lights, and we're showing right in behind them. They don't do what we do. So Airy saw this about 4 years ago. We were at a conference in Las Vegas, and the Airy guys all come in and they got their badges that are about this long, and they're all in suits and they all speak with a German accent because they're from Germany. And they said, so what is this relamp? So we gave them the tour and told them the whole thing. And one of the guys said to Pete, we should have done this. And I said, right. And a lot of other people have said that too. When they see it, actually, that's one of the things that Feynman said, Richard Feynman. He said, you know you have a good idea if somebody can tell you about it in their own words. And so I've had a couple of people tell me, oh, that's really cool. I should have thought of that. You know, because it's pretty obvious, isn't it? Well, we didn't think of it. We had some other guy who wasn't in our business at all and knew about movie lights. And he said, have you thought about those big lights that are hanging in Hollywood? And Pete knew all about them. He knew what they were. And he said, why didn't I think of that? It's right in front of me. So it's always nice to have somebody from left field come into your world and tell you something, because you're the easiest person in the world to fool. It's the easiest thing for you to do, to fool yourself and make yourself think that you know. You know, oh, I know that. Oh, don't tell me how to run my business. Oh, I don't think they would need that. You have to listen. And if you listen, you succeed. If you don't listen, I don't think you will. And if you don't learn to ask questions, it's going to be really slow for you. So you need to pay attention to that. Yep.
What's the switch on the front of that for?
Okay, the switch is for, it's a good question. Studios care about noise. A lot of them are intimate, and they're shooting, I don't know, a drama. I say it's a Netflix drama. They don't want a lot of noise, because it's hard to get rid of it. Once you got it, it's hard to get rid of it. So they want quiet. So the S, there's two settings here, L and S. S means studio. And all that means to this instrument is that the maximum fan RPM is limited. And it's really logarithmic. I don't know if you know much about sound, but it's very logarithmic. The ear is very logarithmic. If you drop the sound by 10% as far as the fan is concerned, your ear will perceive more than that, and that might be enough, and usually is. So when you put this in S mode, and you put it in the fixture, and everything starts getting hot and hot and hot and hot, the fan's speeding up, the fan reaches that S limit. It won't go any higher. So if it reaches that limit, and it often does, in the fixture, now what happens? The fan's out of horsepower, the LED and the heatsink are still getting hot. Now what? Are you going to let it melt? And if you do, the customer's going to say, hey, my light melted. So we have something we call, it was on the last slide there, it's called adaptive dimming. It simply means that when we're in S mode, because the customer wants to be quiet, that means that the fan can't go to full RPM. That means the LED can't be cooled at full tilt, full brightness. The fan can't handle all that heat. So there's a program, part of the program here is to dial back the intensity of the LED. That's why it's called adaptive. Dial it back just to the level where the fan can keep everybody happy. So in L mode means location. The fan can run wide open because you don't care. If you're outdoors, there's a lot of other noise, you don't care. So L and S are location and studio. And that's a great question because I hadn't told you about adaptive dimming. And that's what really saves this thing. So when Pete first proposed this, I said, oh, they'll never go for that. He said, just do it. I said, they'll never go for it. You put a switch on here, and so the light won't get as bright, and when we go into adaptive dimming, because we want to be quiet, the intensity starts coming down. They'll go bananas. They'll say, what happened to my light? And Pete says, no, that's not true. Modern cameras that you buy, anybody can buy, especially professional cameras, are extremely sensitive to light. And so this old notion that we had in Hollywood, in the old days, when we were shooting 35mm film, you really did need a lot of light because film wasn't that sensitive. Most of the film they used. It was ASA 25 and stuff like that. So nowadays, with modern digital cameras, you don't need a ton of light. What you really need is quality. You need really, really good light. And there's an index that is applied to this called CRI. It means Color Rendering Index. And it's really a measure of how good this is compared to sunlight. So sunlight is perfect. It's got the whole spectrum. This is almost as good as sunlight. CRI of 100 is sunlight. That's the reference. This thing is CRI 96. Pretty good. So that's what people care about now. So when we go into adaptive dimming and we bring it down, as long as it's not abrupt, the lighting director knows about it. He says, oh, okay, I see what's happening. We're hot in here. All right, hold on a minute, everybody. They recalibrate. They push probably one button on their camera, and they're back in business. So Pete was right. It wasn't a big deal. I thought it was, but it wasn't. And it's all because of modern cameras and the fact that absolute light is not so important anymore. What's really important is control and quality. Anything else?
How long does it take for the cost to break even? Like a couple of years or something?
To do what?
The cost to break even?
Oh, the
Buying
cost to
one of
break even?
these versus the
It
spreadsheet?
depends. Go look at the spreadsheet. It's so much fun. I can summarize it for you. If you use it, let me think now.
I think it's at 7.8.
If you use it more than 300 hours per week, no, is that right? No, wait a minute, 300 hours a month. The payoff period for a normal person can be as little as 6 months. And if you're just a hobbyist and you're using it occasionally, maybe 3 years. But when we show that 6-month number to people, they say, oh, I use my light more than that. Well, you'll pay it off faster than that. We were conservative. So, yeah, it's amazing. You don't realize how much money you're throwing away on all that stuff I named until you start looking at a spreadsheet. You say, yeah, I do that, that's dumb. And then you realize, oh, with this you don't do any of that, really. So, it's, yeah, it's great. Thanks a lot. More questions? Everybody wants pizza, can you smell it?
All right, and now it's now 5:45, and I would like to thank Jenny for giving us such an instructive and interesting talk. Thank you very much.